for sure happy. I know they're feeling blessed today, 5-0, looking
Five
at
and
the
zero.
record, feeling beautiful. Shout out your record. Shout out your quarterback. Shout out your MVP. But we got 17 championships. It's a whole different bag over here.
Yeah,
Whole
yeah.
different bag.
So who else commented about the Seahawks?
A smart man.
Yeah, well, I'm a Vikings fan, so I'm a little pissed off today.
Man, you in Minnesota, man.
Me and Minnesota. That's right. It's
What
okay.
situation did you
It was
walk into a
close.
game looking at Kirk Cousins like he was gonna do it for you?
He almost did it.
See, but I thought almost only counted in grenades and horseshoes, not
Yeah.
football.
No. Yeah. I agree. I agree.
It's like I'm not here telling you we almost won a championship. Whew, God damn, I don't know what that stress would
Story
feel
of
like.
my life as a Minnesota sports fan. That's
I empathize
lots of
greatly with
almosts. Yeah.
you. Man, pain.
Yep. Pain. Pain. Oh, I gotta clean up my notes here and we'll get started. Yep, it's almost 10 o'clock. Almost time to go. Almost time to rock and roll. I had some technology problems at 8 o'clock. Hopefully, those are all ironed out now and they won't affect us. I'm sharing my iPad, see if that works. Oh no, don't tell me. Oh, there we go. All right, October 12th. Calc 1. So, just by way of announcements, grade reports are going to on their way. I ran into a problem over the weekend. I think I figured out how to do it. And I'm going to send them to your CI email address. So remember, this is for you to give me feedback as well. If I got anything wrong, let me know, and I'll try to fix it. Other announcements. I think we're about halfway through the semester, right? This is about midterms time. We're not taking a midterm exam. We're going to just rely on these learning target quizzes, but we're halfway through. I think we're in a good place in the class. We've kept a good pace. So, I'm happy about where we are. Some days I feel like the semester's dragging on. Other days, like today, I felt like it's going fast. I don't know where half the semester went, but I guess that's the way life works sometimes. Anything else people want to share as we get started? Cynthia, do you have anything for the group?
Just a quick reminder about tutoring drop-in hours on Friday from 12:30 to 1:30, and all of my hours are listed on the homepage for the course in Canvas.
Yeah, great. So drop in to talk with Cynthia if you can. You're welcome to talk about learning target quizzes with her and get her feedback on your work. I just ask that if you're there with other people, if you haven't taken the learning target quiz that somebody else wants to talk about, please remove yourself from that conversation. It would be sort of a violation of academic integrity for somebody who hasn't taken a quiz to talk about it with somebody who has. So just be careful about that. Be sensitive to that. And I know Cynthia will be too, but sometimes we just make mistakes and we overlook it. If you make that kind of mistake and you find yourself in a conversation with somebody about a learning target quiz you haven't taken, just let me know. So mistakes may happen, but I just wanted to let you know that it's okay to talk with other people about your learning target quizzes if they've taken them already. And Cynthia, you can talk with her about any one of the learning target quizzes you want. Okay. So let's talk about derivatives. One other thing, and this might be worth writing down on the iPad screen I'm sharing. Miller will look at Jamboards this afternoon. So last week I asked you to complete 5 of those Jamboard exercises by today. And so today I'm just going to take a look at the Jamboard URLs that I collected in class on Wednesday and see how you're doing. If you haven't completed that with your group, you've got a couple hours after class probably to go finish those up, but I just want to let you know that I'm going to do that. You don't have to turn anything in. I've got the URL. I'll just go look at it and make a couple notes. But I just wanted to remind you that was happening. Where's the chat? Somebody threw something in the chat. Yeah, okay, Cynthia. Reminding us about the drop-in hours for her. Would anybody here like to talk about the Jamboard activity? You want me to walk through it as like a warm-up to where we are?
Yeah, actually, I would appreciate that.
Yeah?
Professor.
All right, let's do that. Now, what I want to do, I did that with my class this morning. Let me try to revert it to a point before I made any changes. Let's see if I can do that. It doesn't look like that's easy to do. Okay, pardon me here while I think for a minute. Thinking. Sometimes the old thinker is slow. Sometimes the Jamboard is slow. Almost ready. So what I'll show you on the Jamboard is I'm going to show you, I'll walk through kind of what I wanted people to get out of it. And then I'll sort of take it to the next level and kind of tell you the kind of skill that I want you to develop. But before I go any further, okay, we are recording, right? Okay. So I'm almost ready. Let me check a couple more things. As the Jamboards load very slowly. Okay, I think I'll just leave it at that. So let me share my browser. Okay, so here's the Jamboard. Here's the first frame of the Jamboard. You can see my tangent lines laying down here, getting ready to use. So let's just quickly go through what I wanted you to do. What I wanted you to do was pick some points on a curve, throw the tangent line, move the tangent line into place, and and rotate it so that this line becomes like a tangent line, has the right, kisses the graph, right? And then estimate the slope of that tangent line, and then plot that point, because the derivative function is a function whose values are actually the slopes of tangent lines to the original function. So this is supposed to be an activity to help you really feel good about that association. So let me show you how I'll do this. So I'm going to select this big marker. So the first thing you do is you pick the points that you want to estimate the derivative at. And the first point I want to choose is the one where the tangent line is horizontal. So that's right around here. So I'm going to plot that point of tangency. And let me grab a line there. You can see horizontal tangent line there. And a horizontal line has slope 0. And so I'm going to plot that point. So there's my first point on the derivative of the blue curve, right? So if the blue function is f, this is my first point on the graph of f prime. So next I'm going to pick another point of tangency, say over here, and let's move one of these lines over to become the tangent line. I've got to change the slope to be about what I think is appropriate. So right there, maybe it's a little steeper. Yeah. Okay, and so there's the slope of there's my tangent line at that point. Now the next thing I need to do is estimate the slope of this tangent line. So I'm going to look at this triangle here and look at the tick marks on my horizontal axis and my vertical axis. And from those tick marks, do my calculation. So I'm going to grab a piece of paper here and do the calculation. So here, I'm going to start with this point right here, which looks like it's at about negative 0.1, comma 0. And I'm choosing it because it's on the y-axis. That's an easy value to choose. And it's an approximation. It's not exact. And then I'm going to come down here, let's say to 1. I'm going to look at what's my value here at 1. It's slightly more than 5. So I'm going to say that's like at a 5. Let's say that's 5.25. So at the point 1, I'm at a y value of 5.25. So I want to calculate the rise over run. So my delta y is going to be 5.25 minus 0. And my delta x is going to be 0 minus a negative 0.1. Is that right? Not a point, negative 0.1. It's going to be a 1 minus negative 0.1. So my delta y over my delta x is about 5.25 over 1.1. And so I'm going to say that's about 5. Just we're approximating. And so that's the slope of this tangent line. So I'm going to go plot the point right above my point of tangency, but up at 5. So I think that's right about here. So that's the other point on my derivative, or that's the second point on the graph of my derivative. So let's go plot one more. I guess I have to pick the point of tangency first. We're going to go to the other side of my first point. Let's go here. So next we have to move a tangent line into place. Let's try to give it the appropriate slope. Let's say it looks like that. Move it into place. Yeah, that looks good enough. All right, now I need to calculate the slope of this tangent line. So I'm going to pick 2 points. I'm going to look at this point over here. It looks like we're at minus 0.9, comma 0. So that's this point here. And then I'm going to come down, let's say down here to -2. So we're at -2 and about 5 and 5.25. So -2 and 5.25. So my delta y is 5.25 minus 0, and my delta x is -2 minus a -0.9. So delta y over delta x is 5.25, and my over -1.1. And so that's about -5. And so I'm going to take my point. So having estimated the slope of this line being about -5, I'm going to go find my point of tangency, and I'm going to go down to the y value of -5, and I'm going to plot that point. So what I've done here is I've plotted 3 points that are on the graph of the derivative of the blue curve. And then what your brain is supposed to do, since your brain is really good at seeing patterns, your brain is supposed to think, hey, these points lie on a line. It's a pretty crappy straight line. But it looks like the derivative of this parabolic shape must be a straight line. These 3 points seem to lie in a straight line. And that's in fact what you should be seeing. So again, I will repeat. Through this process of placing tangent lines, estimating their slopes, and then plotting the corresponding point on the derivative, you're supposed to see maybe a pattern forming in the values of the derivative to suggest what kind of function the derivative would be, knowing what you know about families of functions. For some of these frames, it's a little harder than others, but this is a good example of what happens in a quadratic. Is this good? Anybody want to ask any questions about this?
I have a question.
Yeah, Joseph.
So will you always get a linear line from a parabola?
Yes, and I'll show that to you today. Remind me that you asked that question, and I'll try to address it directly. But yeah, it turns out whenever you get a parabola or a quadratic function, its derivative is going to be a line.
Thank you.
Yeah, not to be mistaken with the tangent line. The derivative function is going to be a line. Any other questions? That's a good one, Joseph. All right, let's look at this one and talk about this one quickly. So what I want you to be able to do is develop skills to do what we did on the previous frame really pretty quickly without having to actually draw the tangent lines in. You can get a sense for what the derivative function should look like. So you can sketch it. And so here, this is how a sketch might work. So I'm going to look at this graph, and I'm going to look for the point where the tangent line is horizontal. Because when the tangent line is horizontal, I know it's got a slope 0. And so the graph must go through that point. It must cross the x-axis. And then looking at this curve, I can see, well, here to the right of my point of tangency, the tangent lines, right, they start with slope 0. And as I move to the right, the tangent lines start having a negative slope, and the slopes start getting bigger and bigger. And so that suggests that my derivative is doing something like this. It's going down. Similarly, if I start at my point of tangency and move to the left, I can see that my tangent lines all have a positive slope. And as I move to the left, their slopes get bigger and bigger and bigger. And so that suggests that maybe the derivative is doing something like this. And again, using Joseph's theorem, Joseph's idea that if this is a quadratic, then my derivative is going to be linear, then that's kind of why I'm sketching this thing in a linear fashion. Maybe I've got it sloped a little bit wrong, but I know that my derivative is going to follow this pattern. Negative to the right of my point of tangency here, positive to the left, and growing as I move away from this point of tangency. Growing in the positive direction on the left, growing in the negative direction to the right. So this yellow curve I gave you with this green dot, that would be a decent sketch of a derivative. And this is the skill I want you to be able to develop. Let's look at this one. A lot of you notice this, so let me change this, that when you take a point and you draw the tangent line at that point, that tangent line coincides with the curve. So it has the same slope as this line. So what slope does this line have? Well, I think it has slope 1, if I remember correctly. And so at this point of tangency, the slope is also 1. And at any other point of tangency you choose, the slope of your tangent line is going to be 1. So in this case, the graph of the derivative is just this constant function. Because the tangent lines all have the same slope. Right? They're pretty static along the whole graph. So this is a sketch of the derivative of the blue graph. Here's my sketch of the graph, or the derivative of this blue graph. Notice I started by picking these 2 points on the blue graph where the tangent line is horizontal, and then plotting where that tangent, or where that value of the derivative is. So those are the 2 easiest places to plot. And then between these 2 points, my tangent lines are, the slope of my tangent lines are positive. So I know the derivative goes above the x-axis here. To the right of this point, my tangent lines are all negative. They hit the negative slope, and they get steeper and steeper and steeper. So my derivative here at this point must become negative, and the values of the derivative get bigger and bigger and bigger in a negative direction, because that's what the slopes of these tangent lines are doing along here. Likewise, at this point, when I move to the left, at my points of tangency, the tangent lines, their slopes are getting steeper and steeper and steeper in a positive, well, in a negative way, right? All these tangent lines have a negative slope. And so I know my derivative from this point, as I move left, it's got to have a negative value, so it's below the x-axis. And as I move away from this point, the slopes are getting bigger and bigger and bigger in a negative direction. So that's why this green curve is the sketch of the derivative. So back to Joseph's idea about derivatives of quadratics being linear. Here, this is a cubic, a degree 3. It looks like my derivative is degree 2. So that's an interesting observation, an interesting pattern. I think I'll leave it there. Here's a piecewise linear function. The slope of this piece here is 1. And so the derivative is a horizontal line, but then the derivative on this piece is 0. And so the derivative is a horizontal line. The slope on this thing is negative, looks like a negative 1. And so the derivative is down here. So this is an example of a function whose derivative is discontinuous. And the derivative doesn't exist at these points, right? The sharp points, or at these breaks. So that's why there's these discontinuities down here. So this is what I want you to be able to do. Be able to look at a function and be able to sketch out the graph of its derivative. Doesn't have to be perfect. That's why we call it a sketch. But you should show some of the dynamics that the derivative has, as far as like, where's it positive, where's it's negative, where's it getting bigger, where's it getting smaller, right? And just the best guess. It doesn't need to be perfect, because if somebody asks you for a perfect graph, what do? Anybody?
Use a computer program.
Use a computer program, exactly. Exactly, Cyrus. You should go to Desmos or Wolfram or something like that. Okay. Was that good? Was that helpful? Looking at the Jamboard? Me telling you what I wanted you to get out of it?
Yeah, thanks. I really appreciate it.
Okay. So if you haven't quite finished it as a group, again, you'll have a little bit of time after class today. All right, so what I want to do today is build on these ideas and show you how we can calculate derivatives in a more efficient way. So let me go back to my iPad. So let me write that down. Today, more efficient ways to calculate derivatives. Okay, and so I'm going to give you some new rules for differentiation. And they're going to come in the form of a theorem. Actually, two theorems, I think. And I'm going to focus right now on the second theorem. The second theorem is going to have 4 rules that you're going to have to become very familiar with and understand and be able to use almost reflexively, almost without thinking. The first one is called the constant multiple rule. The second one is called the sum or difference rule. And these 2 rules are very similar to rules that you saw in the limit laws. Okay, so they'll look very familiar. The next 2 are new. They're going to have a new pattern. And the first one is called the product rule. And the second one is called the quotient rule. Okay, so those are formulas that you're going to have to memorize and you're going to have to practice. I mean, again, you need to get reflexively good at these. And by reflexively, I mean, you're going to need to practice enough where you can recognize when you need to use which rule, and you're going to recognize how to use each rule. Okay, and that's particularly important for these last 2 because there will be a formula that you need to memorize. All right, but before I talk about these rules, there's one other theorem that I want to show you, and I'll prove it to you. But I also want to make a note about notation. That's no pun intended. So when we have f of x, that's function notation, right? That's notation for a function. And I've introduced to you this notation. So this is the derivative of f. Okay, and here we're using what's called prime notation. And I want you to think of both of these things actually as nouns, right? They're objects. They're concrete objects. The function, its derivative. But I also want you to be aware of differentiation as a verb, or the idea of derivative as a verb. Okay, and I said the word differentiation, because these theorems, these rules up here are about the process. Okay, and they're the process that give us the result. They give us the derivative. They're going to give us the nouns. So let me just say a couple things about notation for the verb part of this. So I want to introduce you to what's called Leibniz notation. And this is notation that Gottfried Leibniz invented when he invented or discovered the calculus. And it's so good that we're using it today. You will never see anybody using Newton's notation because it sucked. Okay, Leibniz notation is really good, and we still use it. So in prime notation, we write a derivative this way as f prime. In Leibniz notation, we write it this way. Okay. So you can see that it looks very different. Right? This here is the notation for the derivative. And what's cool about this notation is it kind of tells you what variable you're differentiating with respect to. That doesn't seem like it makes a lot of difference today, and it kind of doesn't. What that means, though, is here's the definition of the derivative. And the derivative says you're changing x by adding h. And so you're messing with the x variable, and that's being specified in the Leibniz notation itself. Pretty soon, we're going to be using this phrase, the derivative of f of x with respect to x. Okay, and the Leibniz notation captures that, what you're differentiating with respect to. So in that way, this Leibniz notation is superior to prime notation. Prime notation, it's not obvious what you're differentiating with respect to. In Calc 1, we're lucky because we only have one variable that we're working with. And so there's no ambiguity. But when you get into Calc 3 and you've got functions of several variables, this notation becomes very important. Another benefit of this notation is it allows us to talk about what's called a differentiation operator or operation. And here we're getting this idea of verb, derivative as a verb. And it's this, d dx. And so notice this notation is almost like using function notation where the variable is the function. Or is a function. Sorry, that's so low on the screen. So the input is the function and the output is the derivative. Okay. So differentiation as an operator. And what I'm going to do is I'm going to use this differentiation or this operator notation when I state this theorem that has these rules. Okay. But let me give you an example of how this is used. Compare the idea of taking the derivative of 3x minus 8 with trying to use prime notation at the same time. Okay, so a reasonable person could say, these are two notations for the same thing. Different notations. But we're going to see that keeping track of a prime, right? If you have problems keeping track of negative signs when you're doing calculations, how hard do you think it is going to be to keep track of these little tick marks, these prime marks? So this is really not very efficient. This is a very nice, efficient, and obvious notation to use. Yeah. So let's just do a simple example. Let's take this function 3x minus 8. And let's calculate f prime of x, its derivative function. So watch me use this notation. F prime of x is the derivative of 3x minus 8. So this notation is suggesting that this is an operation I'm going to conduct on this function. And we know from the definition of the derivative that this is the limit as h goes to 0 of f of x plus h minus f of x all over h. And let me do us all a favor. I'm going to copy this onto the next page. Oops, that wasn't good. So continuing, f of x plus h, here we're taking that x plus h and we're plugging it in for x. And so I get the limit as h goes to 0 of 3 times x plus h minus 8 minus 3x minus 8 all over h. And I usually like to pull that h out, so I'll do that here. And then distributing the 3 And distributing that minus sign, we get this. And now we're going to do algebra. And this is the point where we hope for lots of cancellation. So indeed, we see the 8 and the negative 8 cancel. And this negative 3x cancels with negative 3x. And we're just left with a 3h. And here you see, oops, those h's now cancel and we're left with a 3. And the limit of a constant is just that constant. So this shows f prime of x is 3. That's what the calculation shows. And what did I do here? I just showed you how we use this notation, ddx, this operation notation. Before today, you would not have written that down. You would have gone directly from f prime of x to this limit notation. And that's okay. You'll see today why you might do something like this now. All right, I'm almost ready to give you these rules for differentiation. But before I do that, I want to point out one thing about this example. When I wrote down f of x equals 3x minus 8, part of your brain should have been saying something like this. Oh, the graph of that function, this is a linear function, so the graph of this function is a line. So the tangent line at every point to that graph will coincide. So they'll have the same slope. They'll all have slope 3. So the derivative of this thing should be 3. That's what part of your brain should have been doing. Maybe you couldn't hear it, but I want you to start thinking in that way. There's some functions you can't do that kind of thing, but this one, hey, it's a linear function. And so that slope of that tangent line, or that slope of that line jumped out, and you should have anticipated that we're going to calculate a 3, that f prime was going to be equal to 3. So in that spirit, here's another theorem for you. Suppose f of x is a constant function. That is, f of x equals k for some real number k. Then, so this is what the theorem says, then f of x is differentiable everywhere, actually. And f prime of x is 0. So it's 0 everywhere. So if you use the logic that I said part of your brain should be using when you saw this example, if you use that, hey, what's the tangent line example on this? You should say, yep, obvious. You shouldn't question this at all. You should say, this is obvious. Next. So, but I'm here to say, sometimes it's the things you think that are obvious that are in most need of a proof. This isn't one of those, but my job is to tell you that even obvious things ought to be proved. Don't say something is obvious and think people are going to believe you. That's kind of rude. So let's prove this. So we want to prove that the derivative of this function is 0. So f prime is the limit as h goes to 0 of f of x plus h minus f of x all over h. Now I'm going to substitute my function's formula in for that, and my function's formula is really simple. It's just k. So that's k and that's k. So let's sub that in. Pulling that k or that h out. And now is the step when we look for simplification, and it's just staring us in the face. Those two things cancel. And so we're taking the limit as h goes to 0 of 0 over h. But notice, 0 divided by any number that's not 0, that's got to be 0. And our h is a small number that's close to 0, but isn't equal to 0, right? When we're taking limits, our h's are never equal to what we're going to. So we're sure that that equals 0. So we're taking the limit as h goes to 0 of 0. But the limit of a constant is that constant. And so we get 0. And that's what we wanted to prove. F prime is always 0. Okay, so here's our first differentiation formula. Any constant function, its derivative is the 0 function. Any questions about that? So Giovanni, did you just ask this question? I just noticed it. What kind of functions can you not use this with? That was 3 minutes ago. What are you asking about? Can you help me? No? All right, maybe we'll get back around to you. So it's 10:39. We've got 10 minutes before we take a break, so I can at least state this theorem. So here's a theorem. It's about differentiation rules. Oh, let me, yeah, I'm going to state 2 theorems, maybe 3, and burn a little time before we take a break. So here's the first theorem. Let n be a counting number. i.e. n is 1 or 2 or 3 or 4, right? One of the counting numbers. Then the monomial function x to the n is differentiable everywhere, which shouldn't come as a surprise because you know what the graphs of those monomials look like. They're all nice and smooth. They don't have discontinuities, right? They're continuous and they don't have any sharp points. So f of x equals x to the n is differentiable everywhere, and the derivative of x to the n is n times x to the n minus 1. I should have written this down. This is called the power rule. So this theorem is called the power rule theorem. It's the most important theorem in this whole class for you as a learner. You need to know when to use this. You need to know how to use this. It has to become reflexive. It has to come to the point. It has to come to the point where you think this is the definition of the derivative, but then you catch yourself and say, nope, that's not the definition. The definition is the limit definition. Okay. All I'm saying, and I'm saying it badly, super important for you. Maybe the most important theorem in the class operationally for you as you learn this. Conceptually, it's not the most important theorem, but this is really important. So that was one. Oh, so the proof uses the binomial theorem. And so I want to show you the proof. And so maybe I'll show you the proof and then we'll state the other rules after the break. So the binomial theorem, I'm going to do this in a different color. So this isn't exactly going to be the proof. I'm going to explain it. I'm not going to write down the proof. You might have seen Pascal's triangle that looks like this. Have people seen this triangle before? Anybody seen this before?
Yeah.
Yeah. Okay. And so Pascal's triangle, when you want to figure out what number goes in a certain place, you look at the previous row and you add up the adjacent numbers and you get it, right? So Pascal's triangle, if you have 2 symbols and you want to raise them to the nth power, Pascal's triangle gives you a formula for doing that. Okay, so I'm going to come back to that. But let's say x plus y to the 4th power. So this is the 0th row. So I'm going to write that in n equals 0, n equals 1, n equals 2, n equals 3, n equals 4. Okay, so these n's are like the powers here that we're going to take. So the fourth, n equals 4, I'm going to be looking at this row. So what Pascal's triangle tells me is that x plus y to the fourth power expands to x to the fourth plus 4x cubed y plus 6x squared y squared plus 4xy cubed plus y to the fourth. The coefficient on those terms in the expansion are the coefficients that come right from that row. Okay. So if I say I'm going to define a new symbol called C sub n sub k, okay, and that's going to be the kth entry in the nth row of Pascal's triangle. And here, k goes from 0, 1, 2, all up to n. Right, because notice, when n equals 2, there's 3 entries, so I need k to go from 0, 1, 2. There's a formula for these numbers, and the formula is n factorial over k factorial over n minus k factorial, where n factorial is the number n times n minus 1 times n minus 2 all the way down to 2 to 1. This is an important formula that comes up. We use it in Calc 2 toward the end of the semester. We also use it in statistics. So we can check. Let's check this. Let's calculate C for 2. Okay. So C for 2 would be 4 factorial over 2 factorial over 4 minus 2 factorial. So that's 4 factorial over 2 factorial times 2 factorial. That's 4 factorial over 4, because 2 factorial is 2 times 1. So in the bottom, we just have 2 times 2. So when we look at 4 factorial divided by 4, 4 factorial is 4 times 3 times 2. So this 4 can cancel with that 4, and you're left with 6. Okay. So according to this formula, C42 is 6. Now let's look over in Pascal's triangle. C42 is the entry, it's the second entry in the fourth row. So let's go to the fourth row and equals 0, 1, 2, 3, 4. And starting at the left, what's the second entry? Well, here's the 0th entry, here's the first entry, and here's the second entry. Yep, got it right. Okay. So what does that have to do with this? Right, I've got 4 minutes before we take a break. So it turns out when you expand this, x plus y to the n, you'll always have an x to the n at the beginning because you've got 1s at the beginning. And because you got 1s at the end, you're always going to have 1 y to the n at the end. And then in the middle, all these numbers are going to be of the form c n sub k, x to the n minus k, y to the k. Okay. And it's worth pointing out that the next term after the x to the n comes in this column, and it's just n. So let me write that down on the next page. X plus y to the n is x to the n plus n times x to the n minus 1 y plus a bunch of stuff, and you'll get all the way down to y to the n. Okay. And this is because of Pascal's triangle. Okay, so here's the proof of the power rule. I've got 2 minutes. The derivative of x to the n is the limit as h goes to 0 of f of x plus h minus f of x over h. Here, f is this function. So this is the limit as h goes to 0 of 1 over h times x plus h to the n minus x to the n. Right? And here's where we use the binomial theorem up here. And where there's a y up here, we're going to put an h. So we get the limit as h goes to 0 of 1 over h times, okay, x to the n plus n times x to the n minus 1 h plus, there's a bunch of stuff all the way down to h to the n. And then we have this term. And what I'm going to point out to you is that all of these terms have h as a common factor. And that this first term here only has 1, but the rest have 2 or more h's. So after you notice that this x to the n and that x to the n cancel out, what you can do is you can factor out an h from everything, and it'll cancel with the h in the denominator here. So I'll write that out. Lim h goes to 0 of 1 over h times n times x to the n minus 1 plus h times a bunch of other stuff. Okay. And this second term, that factoring that h out, is because all these other terms here, not this term, this one only has 1 h in it, all the other ones have 2 h's. So after we factor out 1 h, it comes out of this first term. All these other terms still have another one to go, and we can factor it out. All right, then that h cancels with that, and we're left with the limit as h goes to 0 of n times x to the n minus 1 plus h times some polynomial in x's. And then by naive evaluation, as h goes to 0, you can take that h and set it equal to 0, and you end with n to the times x to the n minus 1. So that's the proof of the power rule. You don't have to be able to prove this yourself independently. I'm not worried about that. I just wanted to show you this idea that Pascal's triangle comes back in to help us prove the most useful theorem in this whole course. And then I'll make some other comments about this after we take a 5-minute break. But after that proof, you deserve a 5-minute break. Okay? So let's do it. I'm going to set my timer right now and go get a cup of coffee. See you back at the Zoom in 5.
Can you move the slide forward, please, one more?
Right here? Yeah.
Yes, thank you.
me 5 weeks. Yeah, I think that she'll adjust. You just ignore her.
Yeah, she seems to not really pester too much. I mean, the only time she gets pestering is when I take too long to do her WALK in the morning and evening. Like she starts getting mounted and stuff. She never seems to pester me that much.
Yeah.
That's the way she starts.
Yeah.
You're cutting or the notifier.
All right, still got a minute to go. All right, my timer says 5 minutes are done. Welcome back. We just finished proving the power rule. I'm on a slide that has basically the proof of that, but let's, oops. My iPad is going to sleep. Here's the statement of the power rule. Let me copy this and we'll talk about it here. So let me just repeat. Proof is super important in mathematics. And you, in this class, you need to learn to appreciate the role proof plays in mathematics. We've talked about this a couple times. This is the power rule. This is something that I don't expect you to be able to prove. I don't want you to be able to prove. It doesn't help us so much. But this proof is a classic. It's one of the classic proofs in all of mathematics. And it's a, yeah, I'm going to put my nerd on. It's a fun one to know. But for us in this class, what's important is that you know this theorem statement. Okay, and I'll even take this a step further in a second. I'll even put a finer point on it. You need to know this formula. This is the formula for the power rule. Okay, everybody understand that? Indicate that you understand that. You need to know this formula. Give me a thumbs up or a yes or something in the chat. How important is this formula to us in this course? Anybody want to tell me? How important is it?
Very extremely.
Yeah. It's hugely important, right? Very important. You need to know this formula. Okay, so let's look at this theorem for a second. It says let n be a counting number, right? 1, 2, 3, 4, etc. Then the derivative of this function is this. I'm going to take this a step further. I'm going to call this a new theorem. Let n be a real number. So I'm not going to limit myself to counting numbers. Oops. Then, no matter what your exponent is here, the derivative of x to the n is still obeys the same rule, right? We just proved the counting rule or the power rule for these numbers, but it turns out they work for any number. So that's why this theorem is why you need to know this formula. Yeah, so this is what I really want you to know. Okay, this is what you're going to use, right? This formula for the power rule. So let me just do a quick example. Suppose I want to take the derivative of x to the pi power, whatever that is. Well, by the power rule says the derivative is pi times x to the pi minus 1. Okay. That's what the power rule says. We know why the power rule works in these cases. For the simple case where the exponent is a counting number, we don't know why as a class, we don't know why this works. We don't know why this works when we have n any real number. The proof requires stuff we don't have, requires tools we don't have right now. And one of those tools I'll say is called implicit differentiation. But we can't prove this right now, and that's okay, but I'll let you use it. Okay, so first big derivative formula, okay, after having seen the definition of the derivative, okay. Oh, I guess maybe the second one. The first one was this one, this silly one. The derivative of a constant function is a zero function. Yeah. So second derivative formula for the day. Now let me get to the theorem that I promised you at the start of class, the one that has the constant multiple rule, the sum and difference rule, the product rule, and the quotient rule. We can call this the differentiation rule theorem if you want to. So what we're going to do is we're going to let k be a real number. And we're going to let f of x and g of x be functions that are differentiable at some point x naught. Then we can say four things. So the first one is we can say the derivative of k times f of x. So maybe let me say this a slightly different way. Then k times f of x is differentiable. I should abbreviate that at x naught, and the derivative of k times f of x is k times the derivative of f of x. Okay. So this is called the constant multiple rule. I'll write that down here. Constant multiple rule. And what's happening here is that when you've got a constant multiplying your function, it's like you can pull that constant outside of the derivative symbol. Okay, pull that out before you take the derivative. That's what this is looking at here. Constant times the derivative. Second rule, f of x plus g of x is differentiable. So here I'm going to abbreviate differentiable. So the function f plus g is differentiable at x naught, and the derivative of f of x plus g of x is the derivative of f of x plus the derivative of g of x. And then if that addition sign is replaced with a subtraction sign, this same result holds. So let me just point out to you, this is often called the sum rule. So I'll write that over here, sum rule, or sum or difference. And it kind of tells us how we can distribute the derivative action across a sum. So if we're taking the derivative of a sum of things, well, just let's distribute that derivative across. So you can have the derivative of the first, and then the same operation, derivative of the second. So third one, this one's going to be called the product rule. The product of the two functions is differentiable at x, or at x naught, and the derivative of the product is, so here, this is complicated. It's the derivative of the first function times the second function plus the first function times the derivative of the second function. That's the product rule. These first two rules kind of look like rules we've seen with the limit laws before. This one doesn't look like any rule we've seen before. The derivative of a product gives us a complicated derivative. So this is a formula you have to memorize and you have to become good at using. Okay. This is called the product rule. Right, I'm going to give people a second to catch up, taking this down if you're writing notes, and I'm going to swipe to the next page to do rule number 4, the quotient rule. So this fourth rule says if f and g are differentiable at x naught, then f over g is differentiable at x naught if the denominator doesn't vanish at x naught. And if it's, since it's differentiable, it's good to have a formula for the derivative. The derivative of the quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. Okay, so these are the 4 differentiation rules. I guess I should write this down. This is called the quotient rule. These are all formulas that you need to practice a lot and get very good at, reflexively good at. So let's just recap this, and I'll do it in prime notation this time. We have the constant multiple rule and the sum rule. I'm not going to rewrite those, but the derivative of a product is the derivative of the first times the second plus the first times the derivative of the second. And the derivative of a quotient is the derivative of the first, derivative of the top times the bottom minus the top times the derivative of the bottom, all over the bottom squared. What I want to point out to you in these two formulas is the following. The plus sign here makes you happy because it means that this expression, there's a commutativity here. It doesn't matter if you write this term first or this term first, okay? It means, yeah, there's not a specific order that you need to write these things in, right? Derivative of one times the other, and then do it the other way. The derivative of the other times the other times the derivative of the one, okay? That's not true in the quotient rule. Because there's a minus sign here, your first term always needs to be the derivative of the top times the bottom. And then you subtract from it the top times the derivative of the bottom. If you get the order of these two terms mixed up, your answer is gonna be off by a minus sign. Okay, so just be aware of that. That's where a visual check, like a plotting a graph to check your work, really comes in handy, because if the graph you get is flipped upside down, it might be that you did the quotient rule wrong. And the bottom is always a positive number, so it's not going to affect the sign. Okay, so just two notes to know about the product in the quotient rule. And I'm sitting here, I probably shouldn't do this, but I'm going to do it anyway. Let's write these in Leibniz notation.
Dr. Miller,
Yeah.
would it be possible to also see how Leibniz notation would compare to Newton's notation? Because I hear you say it's awful, but like, I want to see just how awful.
Yeah, let me see if I can find some pictures of Newton's notation. It's a good question. I'm sure I can find something, and I'll try to bring it to class or make a post on Canvas about it. All right, Elizabeth? Okay. So here's the product rule in Leibniz notation. You could put in the independent variable if you wanted to, but this is just has them dropped. And then the quotient rule would look similar: df dx times g minus f times dg dx all over g squared. Okay. In the statement of the theorem, I was using kind of operating representation. All right, so I guess right now we come to the point where we should do some examples, right? I'll see some examples of using these theorems. I know I do. So let's do this. We started out class with this function, and we used a limit definition of the derivative to calculate it. Now let's use the differentiation rule, see if we get the same thing. So f prime of x, right, that's the derivative of 3x minus 8. So the first rule we can use is, we've got a difference of two terms here, so we can use the difference rule for the derivative. And so we can rewrite this as the derivative of 3x minus the derivative of 8. And then we can use the theorem we proved toward the start of class, where the derivative of a constant function is always 0. And so we can write that derivative of 8 is 0. And then on the first term here, we can look at this, and there's a constant, right? The constant 3 has a constant multiple. I could pull that out. Oops. So I get 3 times the derivative of x. And now x is x to the 1, so I can use the power rule to differentiate that. So I get 1 times x to the 0. And x to the 0 is the number 1, so this is 3 times 1. So I get the number 3. And that's what we calculated before. So mathematics is consistent, and that's a good thing. Let me show you something else. This one's kind of fun. let's calculate the derivative using these differentiation rules and not the power rule. In fact, we'll use the product rule to calculate the derivative of x times x. So now notice what we want to get is 2 times x to the 2 minus 1, so that's 2x. That's what we want to get from the power rule. Let's see if we get that with the product rule. Okay, so the derivative of a product, so here's my f and here's my g. It's the derivative of the first times the second minus the first times the derivative of the plus the first times the derivative of the second. The derivative of x, we calculated that over here, right? The derivative of x, we calculated it to be 1. So here the derivative of that is 1. So 1 times x plus x times 1. And sure enough, there we go, 2x. Mathematics is consistent again. So this shows that we don't need that power rule necessarily to calculate the derivatives of powers of x, but certainly it's easier this way. It's easier with the power rule. And then the power rule also, this only works for counting number multiples of x. The power rule, as I said, works for any exponent. Let's do this. What's the derivative of x squared plus x? Well, first we use the sum rule, right? Because we got that plus there. So that's the derivative of x squared plus the derivative of x. The derivative of x squared using the power rule, is 2x to the 2 minus 1. The derivative of x is 1. So we have 2x plus 1. Now, at a point pretty soon, you're just going to be able to look at this function and say the derivative of x squared is 2x, and the derivative of x is 1. You got a plus here. And so you're kind of going to be able to jump right to the 2x plus 1. But until you do a lot of practice, I would highly encourage you to write out all the steps for the differentiation rules so you don't get too confused until you're confident. Here, and let's just double check to make sure that this is doing what we think it's going to do. Whenever we learn something new, it's kind of nice to check work with different representations of functions. So let's look at a graph, what these things look like graphically. So I'm going to call up Wolfram alpha, and let's plot x squared plus x, and then we calculated its derivative to be 2x plus 1. Let's plot it on -3 to 3 and see if this looks the way we're supposed to. So I typed it in correctly and Wolfram understood it correctly, and here's the plots. Blue here is the x squared plus x, and Wolfram alpha decided to factor it. That's fine, it's its prerogative. And 2x plus 1, that's what we calculated. So this makes sense. So here's a graph of our function. Look at where its tangent line is 0, right here. And look at what the purple graph is doing. It's crossing the x-axis. That's exactly what we would hope to see. So far, so good. To the right of this point, my tangent lines their slopes are small, but they're getting bigger and bigger in a positive direction, right? Because my tangent lines have positive slopes, and they're getting steeper and steeper and steeper as I go to the right. And sure enough, the graph I plotted here, 2x plus 1, its values are positive and getting bigger and bigger as I go to the right. So those ideas are lining up. It's doing what I think it should do there. Let's look at this point and go to the left. As I go to the left, my tangent lines over here all have negative slopes. And look at my purple graph. Its graph is below the x-axis, so that's good. That agrees. And going to the left from this point here, my tangent lines all have negative slope, but the further I go to the left, the steeper my tangent lines become. So their slopes are getting bigger and bigger in a negative direction. And sure enough, that's what the graph of my red curve is doing. So All signs point to the fact that 2x plus 1 is indeed the graph of the derivative of this x squared plus x. Good? People understand that? Okay. I encourage you to do things like that when you're practicing this work. So what I want to tell you next, as I share back my iPad. Come on. You can do it. You can do it. Come on, Zoom. Okay. So what I want to share with you next is this idea that the rules for differentiation allow us to calculate the derivative of any polynomial and rational function. So these are two families of functions that you can calculate their derivatives using the rules I gave you. And it's so much easier doing it that way than with the limit definition. There's so much less algebra that's involved when you use the product rule and the quotient rule and the constant multiple rule and the sum rule and the difference rule than if you were using the limit definition. But I don't ever want you to think, well, here I put the formulas down for the product rule and the quotient rule. Some students like to think about these as shortcuts. And I will say, yes, these formulas are like shortcuts because they make calculating a derivative a lot easier. But I should remind you, and maybe this, I forgot to do this, I should remind you that these come from a proof. So these are ideas that are built on other ideas and built other ideas that came together and formed a proof. So let me show you where this comes from. I haven't done that yet. So let's proof of the constant multiple rule. Okay, so that is that the derivative of the constant of a constant times a differentiable function is a constant times the derivative of that function. Okay. So in this proof, we know k is a real number, a constant, and we know f of x is differentiable at x naught. So the limit as h goes to 0 of f of x naught plus h minus f of x naught all over h. This limit exists and is finite, and we call that f prime of x naught. We want to show that this function, k times f of x, is differentiable, and that its derivative is a multiple of f prime. So this is how we do it. We need to calculate the derivative of this function, and we're going to do it at x naught. So maybe I should do it this way. Let me write this down this way. I'm going to put the parentheses here. So what's the derivative of this function at x naught? Well, it's the limit as h goes to 0 of my function k times f at x naught plus h minus my function kf at x naught all over h. So this is k times f of x naught plus h minus k times f of x naught. And what you see here is that both of these terms in this difference, right? So you've got these two terms, both of the terms have a common factor of k. So I can factor that out. And so now I'm taking a limit of all this stuff, and I've got this thing, this changes as h change, right? This h goes to 0, this term changes, this term changes, but this term is constant, right? This does not change as h changes. So I can use a limit law to pull this constant out in front of the limit. So when I do that, I'm left with this inside. And you'll recognize this is exactly this. And since we started out with the assumption that f of x is differentiable at x naught, that this limit exists, is finite, and equals f prime of x naught. Right? And in other notation, that's that. So we've proved that the derivative of a constant multiple of a function is that constant multiple times the derivative of the function, which is the constant multiple rule. All right, so the reason I do this is, one, to show you how it's done. Two, to show you in the case of this rule, it really flows from the constant multiple rule for limits. This constant multiple rule for derivatives is a direct consequence of the constant multiple rule for limits. In the proof of the sum rule for differentiation, the analogous thing happens. Something like this happens where you use the sum rule for limits. But this formula for the derivative is built off of this knowledge on limits. The same, and as I alluded to, the same is true for the sum and difference rule, and the same is true for the product rule and the quotient rule. Those rules are all proved in a similar way that uses the limit definition of the derivative and then does some algebraic stuff to get the formula. So even though, let's see, even though these rules for differentiation can be viewed as shortcuts, really they've got baked in the original limit definition of the derivative. So don't ever forget that legacy, that connection. It's true they're easier to use these rules for differentiation than the limit definition, and this is a good illustration of why mathematicians are the laziest academics around, because they want to do things in the simplest possible way that are still correct. And so rules of differentiation, they get us the right answer, but in a way that's easier than having to do that limit definition all the time. Okay, let's do another example. Let's do an example of calculating the derivative of a rational function. So here's a rational function. Let's do x squared minus 1 over x squared minus 4. So we want to use the quotient rule. So here's my numerator at the top. Here's my denominator at the bottom. So the quotient rule says the derivative of a quotient is the derivative of the top times the bottom minus the top times the derivative of the bottom all over the bottom squared. All right, so let's use our rules for differentiation on each of these terms. So the derivative of x squared minus 1, that's the derivative of x squared minus the derivative of 1. Then we'll multiply that all by x squared minus 4. And then the next term, x squared minus 1 times the quantity. So just using the sum rule again, or in this case, the difference rule. We can distribute that derivative operation. And then the bottom remains unchanged. So looking at these derivative calculations we need to do, we can see here in the first term, I can apply the power rule, and the derivative of x squared is 2x. We've seen that already. And we can use that over on this term as well. And then the derivative of a constant is 0. So I use that there, and we can use that there. So that means that I have 2x times x squared minus 4 minus x squared minus 1 times 2x all over x squared minus 4 squared. All right, this is kind of ugly. We could stop at this point. Oh, well, we could do something kind of interesting. Let's not stop yet, because I see that there's a 2x in this first term upstairs and a 2x in the second term. So I could pull that out, and then we'd be left with this. Oh, interesting. And then in there, you see the x squareds cancel, and you're left with a -3 upstairs. And so we get a -6x all over x squared minus 4 squared. So normally it'd be okay just to leave it right there, unless I ask you to simplify. But having this common factor was kind of tempting, and it paid off, right? It really simplified. But let's see what Wolfram Alpha says about this. Let's go look and see its plots. So I'm going to share my browser with you, and I'm going to put in the two functions. So our original function was x squared minus 1 divided by x squared minus 4. And our derivative function was -6 times x divided by x squared minus 4 quantity squared. And let's do this on, let's do this up from -4 to 4. Now let's do it from -6 to 6. Let's see if Wolfram interpreted our functions right. Yep, so this is what we started with, and this is what we ended with. That's the interval. All right, so the blue is our original function. The purple is our calculated derivative. Let's look at this picture to see if it makes sense. So original function, let's start with this blue part, this branch. Here's where the tangent line is horizontal. Does my derivative function cross the x-axis there? Yep. See, it crosses the x-axis right here. Okay. So looking back at the blue curve here at this branch, as I move to the right, my tangent lines, they all have a negative slope. And as I move to the right, their slope gets bigger and bigger and bigger in the negative direction. And that's exactly what my derivative function is doing. My derivative, the graph of my derivative is below the x-axis, and its values are getting bigger and bigger and bigger in the negative direction as I move to the right. My blue function here is symmetric. It's kind of doing the opposite thing to the left. As I move to the left, my tangent lines are all positive. And as I move to the left, they're getting steeper and steeper and steeper. So you can see that's exactly what my purple curve is doing. To the left, my purple curve is above the x-axis, so values are positive. And as I move to the left, they're getting steeper and steeper and steeper. The values are getting bigger and bigger and bigger. So I believe that this part of my graph is right. The purple thing is doing what a derivative does, the derivative of the blue thing would do. And you could look at these two branches and compare them and say, oh, that seems reasonable. Right, so here, look at this. The tangent lines, as I move to the right, they're all have a negative slope. But as they move to the right, the slope's getting closer and closer to 0. Well, that's exactly what this purple curve is doing. Slopes are all, the values are all negative, but the negatives are getting bigger and bigger and bigger and getting closer and closer to 0. So that looks good. And then the similar thing is happening over here. So this evidence tells me that my calculation is correct. I don't need to go back and see where I made a mistake. Okay, so this is the kind of stuff that I want you to be able to do You've got these derivative formulas, constant multiple rule, sum rule, difference rule, product rule, quotient rule. Now your job is just to practice the heck out of these things. In class on Wednesday, I'll start with a chain rule, and yeah, that's the next rule that we'll talk about. What should we do next? You want to see another example?
Yes, please.
All right, let's do some more examples. So I'm going to go back to my iPad. So let's do this together. So why don't you do this? So let's say I give you the function 3 minus x to the 4th plus 2x squared. I want you to take a minute on scratch paper and calculate its derivative. Use the rules I told you and calculate the derivative. And then I'm going to give you a minute to do that. I'm going to turn my timer on. And then, then I'm going to ask people, we're going to do the 3, 2, 1, go, throw it into chat. So do the calculation for the derivative, type it up in chat, and then wait for me to do the 3, 2, 1, go thing so a bunch of people can share it at the same time. All right, so I'm going to resume my countdown. 1 minute. And maybe not everybody's going to get it, but everybody will get part of it, and we can look in the chat to see what answers people give. Twenty more seconds. All right, my timer just said 1 minute is up. So those of you who calculated something, type into chat what you calculated. I'm going to do the same thing, so y'all see them at the same time. I see, and then people can see how I type it too, if that's any question. All right, and so let's, I'll share it at the same time. Ready? 3, 2, 1, go. Okay, everybody looking at that? What folks shared? So there's lots of consistency in there. So what you just have to be careful of there is the difference rule, right? And you know, the signs, S-I-G-N, right? The signs kill me all the time. So 2 of you have the wrong sign on the cubic term. Right, it should be -4 times x cubed plus 4 times x. Okay. Anybody have any questions about that? Want to do another one? How about, let's differentiate. What should we do? X to the 20th plus 12 x to the 10th plus 17x. So take a minute and differentiate that. Oh, I'm going to add another. There we got a degree 20 polynomial with 4 terms. Oh, I didn't start my timer. Let me start the timer. Set it for 1 minute. When you get something calculated, throw it or type it into the chat, but don't hit enter until we all are ready to go. $25 seconds more. Five seconds. Okay. Oh, should I type it too? You want me to type it in too? I'll type it in too. So let me type it in and then we'll do 3, 2, 1, go at the same time. Okay, everybody ready? 3, 2, 1, go. So I'm looking at them. Yeah. Looks pretty good. Oh, I put in a minus sign where it should have been a 0. Yeah, so dumb mistake on my part. Yeah, looks good. Okay. And let me point out, having the power rule and the sum rule is so nice because can you imagine doing the limit definition of the derivative with the polynomial to the 20th power? That would be royally tedious, a royal PITA, right? But with our rules, it makes it so much easier, right? So much nicer. You're welcome. Let's do it. Let's do a quotient rule. So let's say P of X is the function 3 minus X squared over X plus 2X squared. Okay, what's P prime? Take a minute to figure that out. I will figure it out on another piece of paper. Oh, that's gonna be gross to write out. You're gonna have to have a whole minute just to type that in. I see no way to simplify that. Yeah, let's not bother typing it in. That's a pain. But you can do this. Type in the denominator. What's the denominator? I'm going to do 3, 2, 1, go for the denominator. And then I'm going to ask another question about the numerator. But so the denominator, 3, 2, 1, go. Type it into the chat. And when I say go, hit enter. So what is it? 3, 2, 1, go. Thank you, Alejandro. I was worried nobody's going to do it. Yeah, that's exactly right. The denominator is the denominator that we're given, and you square it. So pretty simple. So here's the next question. The numerator, so true or false? True or false? The numerator is a polynomial. 3, 2, 1, go. Yeah, what is it? So, Cyrus, something can't be kind of true, right? It's not politics. It's math.
Well, the reason I say that is because it's made up of four groups of numbers that can be multiplied together to make a
Yep.
polynomial.
Yep. So polynomials are cool because if you take two polynomials and you multiply them together, you still get a polynomial. You take two polynomials, you add them together, you still get a polynomial. So this is a neat property in mathematics, the fact that kind of polynomials really get along with one another. And so in the numerator, right? So here's another cool calculus fact about polynomials. And this comes from the power rule. If you take the derivative of a polynomial, you know you get back a polynomial. So the derivative of a polynomial is a polynomial. So from the quotient rule, the numerator of a rational function is always going to be a polynomial, because the numerator and the denominator of a rational function are polynomials. The derivative of polynomials are polynomials. So if you look at what you get at the numerator, that's got to be a polynomial. So the answer to the question, is the numerator a polynomial? The answer is yes, or true. It is true. So here's the next question. What's the degree of the numerator? Think about it for a second. And if you've done the calculation, you'll see it. But because the numerator is a polynomial, it has a degree. And we're going to play 3, 2, 1, go, and with what degree it is. So what's the degree of the numerator in this problem? 3, 2, 1, go. Nobody's going to play? Nobody did it? Yeah, I thought the degree was 3, but there might be a term that cancels, so it could be 2. Yeah, I didn't mean for it to be a trick question, but it's no bigger than 3. The degree is no higher than 3. So anyway, this was a hard problem to do over Zoom. I will write down my answer on the iPad so you can see it. I've got minus 2x squared times the quantity 1 plus 2x minus the quantity 3 minus x squared times the quantity 1 plus 4x. So on the question of the degree, you can see over here, these two terms multiply to be a negative 4x cubed. And it looks like over here, these two terms multiply to become a minus 4x cubed as well. But then that minus sign changes the sign. So it looks like those cubic terms cancel. And so the degree looks like it'll be 2. But the point of this problem wasn't exactly, I didn't intend it to be a lesson on polynomials, though that is a good lesson. It's using the quotient rule, right? The derivative of a quotient of two things, it's the derivative of the top, which in this case is minus 2x squared, times the, I factored out an x, times the derivative of the, oh God, I'm making this too complicated. I should have written it like this. So derivative of the top, which is a minus 2x, times the bottom, which is that, minus the top, times the derivative of the bottom, all over the bottom squared. Okay, so I think with that, I'm going to call it a day. Clearly, my brain is a little bit fried. Practice these formulas, these rules. There's lots of practice problems in the textbook. Practice them until you just can't do anymore. The faster you can recognize when these rules get used, the better, the more confident you'll be. And I'll just repeat, next time we're going to talk about the chain rule. So that'd be a good thing to read about before we have class on Wednesday. Okay, that's it. I'm calling it a day. Thanks, everybody. Stay well, stay healthy, stay cool. It's going to be warm, at least down here.
Have a good day, Professor.
Thanks, man.
Okay.
Thank you, Dr. Miller.
You bet. Thanks.
Thank you.
I had a question.
Yeah.
L4, was there gonna be retakes for that quiz? Because I noticed on for where the quizzes are, there wasn't a retake that was like there.
There's not one available.
No, I just saw L4.
Oh, is that the precise definition of the limit?
Yeah.
All right, let me. I will make another one.
Okay.
And then would like me to email you when that's ready?
Yeah, that'd be great. I just wanted to like talk to you too, because I've emailed you a couple of times and I'm not sure if my email's going through to you. One was just regarding the book, because I've been having troubles trying to like, my book would automatically lose connection after like a minute. Like it would just, like. Oh.
That's weird.
Yeah.
Which book are you talking about?
The calculus book, the one that's like, I downloaded it from the syllabus.
Okay, good. And so you'd have a PDF and it shouldn't disconnect. Anyway,
yeah, it's just when it downloads from a Microsoft, like on a browser.
Oh.
Yeah. And then I was just like, you know what, I'm just going to try to use it from, the actual Canvas. But when I do that, Canvas, for some reason, takes a long time to load the pages. So it's like difficult to like go between the two. And I just wanted to let you know that I emailed you about.
Oh yeah. So no, I didn't see that email. But what you should do is that when you go, let me look at our course Canvas page. And let me look in the files section. Yeah, so there is a copy of the PDF of our textbook on our Canvas site. And you can download that to your computer. So I would recommend that you download that file to your computer so you can read it even when you don't have the internet on.
Okay, because I did that and it downloads, but for some reason, all of my books, when they download, they open up the Microsoft browser. And I've had that for multiple classes, for like my Spanish class and like my chemistry class as well.
What kind of computer do you use? It must be a Windows machine.
Yeah.
Do you have Adobe Reader on your computer?
I don't, but would that help?
So Adobe Reader it's a free PDF reader that people all over the world use. So that could help. So I'd go try to download a copy of Adobe Acrobat. Sometimes they call it Adobe Acrobat Reader.
Okay.
Let's see. Yeah. So let me throw a link in the chat that seems like it might work for you. Now, if you open this link, it should bring you to a page that will recognize what kind of computer you have and gives you links to download the correct version. For me, there's like 3 columns, and the middle column lets me download the free Reader app.
Okay.
So try that. Sometimes, let me look for one more thing. So there's a way you can set your browser so that it does read your PDFs, but you want the opposite. I would download that PDF reader and see if that changes the way your computer behaves. And so it should allow you to read all your PDFs without the browser opening.
Okay, sounds good. I'll give it a try. I'll let you know if it works.
All right, give that a try. And sorry I missed your message. I don't know what happened.
No, it's okay. I noticed it's been happening because I think I sent you an email like 2 weeks ago, but then you answered the question in class, so I just didn't bring it up.
Yeah, okay.
The bug happened.
Sometimes people try to send me messages through Canvas, and sometimes they get lost. So if make sure you're sending it to me directly, and it's more likely to get to me.
Okay, sounds good.
Okay.
Thank you
All
so
right.
much.
You bet. Have a good day, Rihanna. See you Wednesday.
Bye.